Hello everyone! Today I'm going to present you our paper titled PSO-Based Performance Optimization Procedure for Current-Controlled Switched Reluctance Generators in Wind Power Applications. The authors of this work are me, Felipe, Professor Rodrigo, and Professor Hilton from the Federal University of Santa Maria. Our presentation is going to be structured this way. I'm going to first present you an introduction, then talk about the switched reluctance generator-based wind energy conversion system, present a firing angle optimization procedure based on two different approaches, then show you some simulation results and the conclusions about our work. So first, the introduction. Increasing environmental concerns have pushed towards the adoption of renewable energy conversion systems. In this sense, wind energy conversion systems are becoming very popular. An alternative for electrical machines used in that kind of system are the switched reluctance generators. They have several advantages, such as being a very simple machine, low cost, and robust alternative. Moreover, they are capable of a variable speed operation, meaning that, for example, in wind energy conversion systems, there would be no need for a gearbox, for example, which would reduce significantly the weight of the overall system. However, there are some challenges still to be addressed, such as problems related to torque ripple and performance optimization, for example. The switched reluctance generator presents two additional degrees of freedom, which are its firing angles, and those two variables can be adjusted dynamically in order to improve performance, for example. However, they have a very complicated analytical formulation. This means it's very difficult to determine the angles in an analytical way. This means that the use of optimization algorithms in order to determine these angles is a very used approach. So I'm going to present you a brief review of the firing angle optimization approaches presented in literature. Papers have presented the influence of such parameters, very thorough analysis, showing that the angles can be adjusted in order to maximize current or minimize torque ripple, for example. Subsequent work has been done in order to provide, again, in-depth investigation and online controllers that seek to adjust the angles according to rotor speed and load, for example, in order to improve the performance of those generators. And we also have seen work based on, for example, computational experiments that seek to minimize the computational burden of these strategies, especially when the optimization is performed offline, which can be very time-consuming. So this paper seeks to provide an alternative using the PSO algorithm in order to speed up the process of the optimization of these variables. So this paper seeks to provide a PSO-based firing angle optimization strategy for current-controlled switched reluctance generators. This means the focus of this work is the operation below base speed. This paper also uses a normalized cost function, which means it considers both torque ripple and copper losses through the use of the current metric. Moreover, this procedure seeks to avoid the use of lookup tables, considering a fixed DC link voltage and ensuring simple implementation. So let's talk a little bit about the wind energy conversion system. So for variable speed operation, an optimal power output profile can be determined by the following equation, where it's directly related to a coefficient multiplied by the speed cubed. Moreover, we can see that the output power in switched reluctance generators is directly affected by the firing angles. This means that optimizing these variables can help to optimize the power output of the generator. So we can see here on the right that we're going to be working in the shaded area where it's below base speed and hysteresis current control is applied. So talking about the firing angle optimization procedures. So for the optimization procedures, we're going to consider dynamic simulations. The machine used in this work is a 1282 kilowatt 157 radians per second machine, and the model will make use of lookup tables containing machine data. The control structure is shown here in the figure, where we are going to use a three-phase asymmetric half-bridge converter, and we're going to use an output voltage controller that is based on a sliding mode voltage controller, and an inner loop controller based on a hysteresis current controller. The cost function is going to be the one shown here, where we're going to use both normalized torque ripple and normalized square RMS current. This will seek a balance between torque ripple and energy efficiency, and we are not going to consider any flux values here, given that considering current is enough, especially in the optimization below base speed. First, we are going to present a fine grid optimization procedure, which will be executed at every 10 radians per second in this speed interval using the following angle bounds. The flow chart is shown here on the right, and it basically will sweep an entire interval for the angles given for a given voltage. Given that that voltage is reached, the metrics of torque ripple and RMS current will be saved, and in the end of the procedure for each speed, the optimal angles will be determined. The procedure is repeated for all of the different speeds, and having the optimal values for each speed value, we then carry out a linear fitting of the optimal angles, obtaining lines for implementation in the digital signal processor, for example. Here we have the results for 80 radians per second, so we can see the contour plot, and approximately in the middle we have the optimal value that has those coordinates, 39.5 degrees and 17.5 degrees turn on and turn off angles. And here we can see the linear regression obtained after all speed values are evaluated. So for this particular proposal, we made use of 1,805 simulations. So the proposal here will make use now of the particle swarm optimization algorithm, and it will seek to improve or reduce computational burden. So we are going to use basically the same parameters, and for the PSO we are going to use 4 particles throughout 20 epochs. So here we have again the flow chart, and here we have the result. So we can see that those 4 particles are able to converge to the minimum value of the contour plot from the last example shown in the background. Moreover, we can see the fitness function, the fitness value decreases throughout the epochs, and we can see that the procedure is very similar. However, instead of sweeping the entire search space, we use the PSO algorithm to more efficiently do that search. Again, several speed values are considered, and the optimal values are fitted to a linear regression. So we can see that here, for the same conditions as the previous example, we made use of only 410 simulations, which means we have a computational effort almost 78% smaller. Here we have a comparison where we can see the results of both the fine grid and the particle swarm optimization approaches. We can see that the optimal parameters are very similar for both techniques, and we can even see that the PSO has some advantages. We can see that in some cases it is able to find lower cost function combinations for the firing angles while making use of much less simulations, as we saw before. We also have here on the right a comparison of the regressions obtained by each method. We can see that they are both very similar. And to finish it off, we have some simulation results. So here we are going to show you some variable speed tests. So the angles are implemented according to the results of the PSO procedure. As we saw before, they have just as good of a result with a much lower computational burden in the offline optimization. And here we have this speed profile. So the speed is going to start at 60 radians a second and will be increased up to 100. The power output of the generator will, according to the MPPT algorithm, be adjusted as well. And the firing angles, while the speed is being adjusted, will also be adjusted in order to maintain the machine in an optimal operating condition. We can see that the voltage controller will be able to adequately control voltage even under the variable speed and variable angle conditions. Here we have the current waveforms. We can see that they are adequately tracked by the hysteresis controller. And lastly, here we have the torque ripple, the output torque waveform, so we can see the behavior of that waveform. So the conclusions and future perspectives of this work. So we presented a performance improvement algorithm for switched reluctance generators through a firing angle optimization approach. We used a new cost function and also used an approach that reduces computational effort significantly. We can see that the metrics considered are both torque, ripple, and energy efficiency, and we were able to successfully optimize the angles for that. The method has some limitations, and more advanced control strategies can be considered in the future. Moreover, the fixed DC link output voltage can be considered in future work to be used in grid-tied systems, for example. Here we have our acknowledgements to the university and all of the other agencies. Thank you very much.